Section 7.2, Applications of the Normal Distribution. We'll look at these two objectives in this section. Objective 1, find and interpret the area under a normal curve. We want to look at standardizing a normal random variable. So suppose that the random variable x is normally distributed with mean mu and standard deviation sigma. Then the random variable z is given by this formula, x minus the mean divided by the standard deviation. This variable is normally distributed with mean mu equals 0 and a standard deviation sigma equal to 1. The random variable z is said to have the standard normal distribution. So here we see a picture of our standard normal curve, or our z curve, with the mean being 0 in the middle and the standard deviation of 1. There is a table that gives the area under the standard normal curve for values to the left of a specified z-score, as shown in the figure below. This table we'll use is Table 5. IQ scores can be modeled by a normal distribution with mean equal 100 and sigma equal to 15. An individual whose IQ score is 120 is 1.33 standard deviations above the mean. So we can calculate this z value. Remember, it's given by x minus the mean divided by the standard deviation. So we have our x value is 120 minus the mean of 100 divided by 15. So we have 20 divided by 15, which gives us our value of 1.33 when we round. We want to round our z values to 2 decimal places always. So here is just a snapshot of our Table 5, and we see that the area under the standard normal curve to the left of z equal 1.33 is 0.9082. So when reading this table, we see the z values on the left here will take into account the first 2 digits of our z value. And then the last digit will be across the top. So to read this, we're going to go down to 1.3 and go over to 0.03 column. And we find our value there in the middle of 0.9082. If we want to find the area to the right, we use the complement rule. Since we know from the table the area to the left, which is what's shaded, is 0.9082, to find the area to the right, which is in this little tail, we'll take 1 minus 0.9082, and we get a value of 0.0918. In general, we have these areas under the standard normal curve. So let's look at an example. We want to find the area under the standard normal curve to the left of z equal negative 0.38. So remember, our Table 5 will give us areas to the left. So all we're going to do is look that up in our table. So we want to go down to our negative 0.3 row and then go over to the 0.08 column and read the value there. And we see that we get a value of 0.3520. So the area to the left of z equal negative 0.38 is 0.3520. Remember, the area under the normal curve to the right of our z value will be 1 minus the area to the left of it. So we want to find the area under the normal curve to the right of z equal 1.25. The first thing we're going to do is look at our Table 5. We want to go to 1.2 and 0.05. And we see that the area to the left is 0.8944. So the area to the right, remember, will be 1 minus that area we found from the table, or the area to the left. So we'll be taking 1 minus our 0.8944, which will give us a value of 0.1056. We want to find the area under the standard normal curve between z equals negative 1.02 and z equals 2.94. To find an area between two z values, we need to look them both up and subtract. So let's kind of generally look at a picture here. Remember that for z, 0 is in the middle. So negative 1.02 is about right here, and positive 2.94 will be here. When I look up 2.94, it will give me this entire area to the left of it. And when I look up negative 1.02, it will give me this entire area to the left of it. The area I'm trying to find is this shaded region here. So what I want to do is take the larger area for 2.94, which we get 0.9984 when we look it up, and I want to subtract the smaller tail off, which is what we found when we looked up negative 1.02, and that was 0.1539. When we do that, we'll get the area in the middle, and we'll see that we get 0.8445. So here's a summation. When we want to find the area to the left of x, we shade the area to the left of it. Then we will convert the value of x to a z-score and use Table 5 to find the row and column that correspond to z. The area to the left of x is the value where the row and column intersect. Or we can use technology to find the area, which we'll see here in a moment. So in this example, a pediatrician obtains the heights of her 200 3-year-old female patients. The heights are approximately normally distributed, with mean of 38.72 inches and standard deviation of 3.17 inches. Use the normal model to determine the proportion of the 3-year-old females that have a height less than 35 inches. So first let's draw a picture. X, our mean, will be in the middle, and we have 38.72. With a standard deviation of 3.17. And we want to look at the proportion that have a height less than 35 inches. So we're about right here, and we'll shade that. We want less than, which would be to the left of our line here. The next step, we want to convert x into z. Using our formula, we'll take 35 minus the 38.72, which was our mean, divided by the 3.17, which was our standard deviation. And we see we get approximately negative 1.17. And now we'll look this up in our table. So we go to negative 1.1 and then over to 0.07, and we see that we get a value of 0.1210. So that indicates that the proportion of the pediatrician's 3-year-old females who are less than 35 inches tall is 0.1210. Now let's look at what to do when we want to find the area to the right of an x value. First thing, we'll shade the area to the right. Then we convert the value of x to a z-score and use Table 5 to find the area to the left of z, which is also the area to the left of x. Once that's found, then the area to the right of z, or x, will be 1 minus the area to the left. And then when we want to find the area between two x values, we see the picture here. We convert both of the x values to z-scores. We use Table 5 to find the area to the left of them both. Then we subtract them from one another. Subtract the smaller area from the larger. So let's look at an example. We still have our pediatrician with heights of 203-year-old female patients. The mean is 38.72 inches and standard deviation of 3.17 inches. In this case, we want to determine the probability that a randomly selected 3-year-old female is between 35 and 40 inches tall, inclusive. So we'll draw our curve, again, with 38.72 in the middle, and go out 1 standard deviation on either side. So we're looking at between 35 and 40 inches tall. And that's the area we want to find. So we want to convert each of these into z-scores. So we do 35 minus the mean divided by the standard deviation. And for the second one, we do 40 minus the mean divided by the standard deviation. So we see we still have negative 1.17 here, and for our second one we have 0.40. Now we want to look both of those up in our table. So remember, looking the first one up as we did previously, we got a value of 0.1210, and that's the area to the left of our 35. And when we look up 0.40, we see we get a value of 0.6554. And so then to find our probability, we'll subtract. We take the larger value, 0.6554, and subtract the smaller, 0.1210. And we see that we get a value of 0.5344. So the probability a randomly selected 3-year-old female is between 35 and 40 inches tall is 0.5344. So let's look at using technology to find areas under the normal curve. First, from the home screen, we'll press the second button, or the orange key, then the VARS button, which is next to the clear key, to access the distribution menu. Then we select 2 for normal CDF. With normal CDF on the home screen, we want to type the lower bound, then the upper bound, then the mean and the standard deviation. So for example, to find the area to the left of x equal 35 under the normal curve with a mean of 40 and a standard deviation of 10, we'll type in a negative E99. To type the E, we hit second, and then comma, then 99. That'll be our lower bound. Our upper bound will be 35, comma, our mean was 40, and our standard deviation was 10. And we see then we get a value of 0.3085. So notice when there is no lower bound, we entered a value of negative E99. When there's no upper bound, we enter a positive E99. The E shown is scientific notation and is selected by pressing the second button and then the comma key. So the example we just looked at, we were looking at the probability that our value was less than 35. So one way to access that would be to say, okay, we have 35 and our arrow then pointing to the left. So we're missing then our lower bound. So we would use a negative E99. If I was looking for the probability that x was greater than 35, then I would type my 35 and notice my arrow is going to the right. So I'm missing my upper bound in this case, so I'd use a positive E99. And if we have a value that's sandwiched between, let's say between 35 and 40, then we have both our lower and our upper bound. And those would be the values we would enter. Objective 2. Find the value of a normal random variable. Let's look at a procedure for finding this. Step 1, we want to draw a normal curve and shade the area corresponding to the proportion, probability, or percentile. Step 2, we'll use Table 5 to find the z-score that corresponds to the shaded area. And step 3, we obtain the normal value from the formula x equals the mean plus z times the standard deviation. And this formula came from our z value, where we had x minus the mean divided by the standard deviation. We simply did a little algebra to solve for x. So in this case, we multiply both sides by that standard deviation. So it cancels here, and we have z times the standard deviation equaling x minus the mean, which we could then add to both sides. So we'd have z times the standard deviation plus the mean equals x. And this formula is the same. So let's look at an example. The combined verbal plus quantitative reasoning score on the GRE is normally distributed with a mean of 1,049 and a standard deviation of 189. What is the score of a student whose percentile rank is at the 85th percentile? The z-score that corresponds to the 85th percentile is the z-score such that the area under the standard normal curve to the left is 0.85. And this z-score is 1.04. So let's look real quick at our table 5. And this time we're not looking along the sides. We're going to look in the middle and find the area that's closest to 0.85. We may want to add a couple of zeros. So we're basically looking for the closest one to 8,500 or 0.8500. And we see that here. So then we look to the left to get the first two digits, which is 1.0, and look above to get the last digit, which is 0.04. So we have our z-score to be 1.04. So now we can use our formula, knowing that x is equal to the mean plus z times the standard deviation. So remember that the mean we were given was 1,049, plus now our z-score we found in the table to be 1.04, and we multiply that by the standard deviation, which was 189. And we'll get a value of 1246. So the interpretation here, a person who scores a 1246 on the GRE would rank in the 85th percentile. Let's look at another example. It is known that the length of a certain steel rod is normally distributed with a mean of 100 centimeters and a standard deviation of 0.45 centimeters. Suppose the manufacturer wants to accept 90% of all rods manufactured. Determine the length of rods that make up the middle 90% of all steel rods manufactured. So let's look at our picture. Remember that we're trying to find the middle 90%. So we want to find our values that divide it out so that we have the middle equaling 90%, which means that we have 10% left over, or 5% in each of the tails. So what this allows us to do, we can look up 0.0500, and we see that we have a value exactly between these two. So let's average the two, and we see that we get a value of negative 1.645. What's nice, we know that our graph is symmetric, so if this z value is negative 1.645, then we know that the other z value is positive 1.645. So let's use these two values in our formula. Remember that the mean was 100 plus our first z value, which was negative 1.645, times the standard deviation of 0.45. So we get about 99.26 centimeters. And our second value, we have 100 plus our second z value, which was positive 1.645, times our standard deviation of 0.45, and we get a value of 100.74 centimeters. So we can interpret this as the length of steel rods that would make up the middle 90% of all steel rods manufactured would have lengths between 99.26 centimeters and 100.74 centimeters. The notation z sub alpha is the z-score such that the area under the standard normal curve to the right of z sub alpha is alpha. So let's look at how we could do this on the calculator. To find normal values corresponding to an area, from the home screen we press the second button, or the orange key, and then the VARS key to access our distribution menu. Then we select number 3 for inverse norm. With inverse norm on the home screen, we'll type in the area to the left, then a comma, the mean, then a comma, and the standard deviation. So for example, to find the normal value such that the area under the normal curve to the left of the value 0.68 with a mean of 40 and a standard deviation of 10, we would type in inverse norm of 0.68, comma, 40, comma, 10. Close our parentheses and hit enter, and we get a value of 44.6770. So if we were wanting to do like the first example we looked at in this objective, we would have done inverse norm of 0.85. This was the 85th percentile. The mean was 1049. And then the standard deviation was 189. So we get approximately 1245.